we place a voltmeter in the circuit that we show here between zinc and copper, the voltmeter reads 1.10 volts. And the reason it reads 1.10 volts is because electrons are moving from the anode to the cathode. So this is the anode over here, and that's the site of oxidation, and the cathode is the site of reduction. And so electrons are going to move through the wire from the anode to the cathode. And so the question is, where does that 1.10 volts come from? Can we calculate that? Why is it 1.10 volts? And so in this video, we're going to look at how to calculate the reduction potential for a cell and how to look up the reduction potentials of individual half reactions. The half reactions for the previous example on the last slide were zinc solid goes to zinc 2 plus 2 electrons, and copper 2 plus gets 2 electrons and goes to solid copper. And so these two processes have voltages associated with them. And so what we want to look up is those reduction potentials. Now, you can see this is a snippet from the appendix in the OpenStax textbook, and it has reduction potentials listed here. These are voltages, all right? So I'll just mark that down, even though it was probably listed. These are volts. And these are the reactions over here on the left. So you can see that chromium, for example, here at the top, is going to have a voltage of negative 0.913 when it is reduced. So chromium 2 plus, add 2 electrons, get chromium solid, and then that voltage associated with it is 0.913 volts. So what we need to look up is we need to look up the transitions of copper and zinc going from zinc to zinc 2 plus and from copper to copper solid, copper 2 plus to copper solid. So in this particular table, I have shown the snippet that contains the copper. So there are 3 copper reactions here. And these 3 copper reactions are all different. They have different voltages. So which one do we want to use? Well, you need to find the one that is the same as what is going on with your reaction. So in this case, copper is adding 2 electrons to become copper solid. So that's what we want to look for here. So this top one is copper 2 plus 1 electron going to copper plus. That's not what we want. The bottom one is copper plus with a +1 charge, adding an electron going to solid copper. Again, not what we want. This is the one that we want right here in the middle. This one contains copper 2 plus going to copper solid. And so this is the one. So we're going to write down this voltage, and it is positive 0.34 volts. So this one is going to be plus 0.34 volts. And here is a snippet from the same table. These are going to be called standard reduction potentials, or in this case it says standard electrode potentials, but these are going to be found in any general chemistry textbook that you pick up. Is going to have this in there. So we want to look for the transition of copper, or not in this case, it's going to be zinc. We already looked up copper. We're going to look up zinc between zinc solid and zinc 2 plus. And so when we look that one up, it is right there. So it's going to be zinc 2 plus 2 electrons goes to zinc solid. Now that is not what our half reaction is. Notice our half reaction is zinc solid going to zinc 2 plus 2 electrons. So it's exactly the opposite. That's okay. We don't want to change the sign on the voltage or anything like that. We're actually just going to write down the voltage associated with the reaction that we find here. So this voltage is going to be negative 0.7618 volts. So negative 0.7618 volts. To calculate for the entire cell, what we're going to do is we're going to use an equation that looks like this. It's going to be E cell is going to be equal to the E cathode minus E of the anode. And so this is a standard equation for calculating the reduction potential of a cell. And you'll notice that there's these little zeros here. I should mention that these little zeros are going to be standard conditions, just like these were standard conditions when we looked at thermodynamics. Had standard conditions. We had delta H, 0, right? Delta G, 0, stuff like that. These little zeros represent standard conditions, which under the thermodynamic standard condition would have been 1 atmosphere of pressure, 25 degrees Celsius, and 1 molar concentration. So that's going to be the same here. So these reduction potentials are all listed at standard conditions. So now what we're going to do is we're going to write down the numbers that are associated with the reduction potentials for the anode and the cathode, and that's going to give us the value for the whole cell. So that's how we calculate the 1.10 volts from the first slide of this video. So let's go ahead and write those numbers down. This reaction is going to be calculated using the cathode of copper and the anode of zinc. So we're going to write down E cell equals reduction potential of the copper minus the reduction potential of the zinc. So those values, we can go get them from the table. They were 0.34 volts, and then it's going to be minus a negative 0.7618 volts. So the final answer for this E cell is going to be 1.10 volts. So that is telling you that if you wanted to, for example, change the voltage of a particular cell, one of the things that you could do is change which metals you use in the cell. So, for example, some metals have a very high reduction potential, some have a rather low reduction potential. So the bigger the difference between them, the bigger the voltage of the cell will be.